Deep inside every transformer model, there's a kind of secret weapon that helps make the whole thing work. It's called normalization. But when you look closer, you find this really fascinating puzzle, a battle between two different techniques, layer norm and the absolute legend, batch norm.
Okay, let's really get into this. Batch normalization, or batch norm, is a giant in the AI world. Seriously, it's the default go-to move in computer vision, and it completely changed how we train deep neural nets. And yet, when you peek under the hood of a transformer, which is the architecture that powers pretty much all modern AI language, it's gone, vanished. So you have to ask, why? Why would this legendary tool be completely rejected by the models running things like ChatGPT? That's the mystery we're going to solve.
So, to figure out why transformers gave BatchNorm the cold shoulder, we first got to understand why it was the champ to begin with. Let's do a quick breakdown of what it actually does and why it was such a game changer. So, first things first, why even bother with normalization? Well, think of it like this. Training a huge neural network is a chaotic process. Normalization is what brings order to that chaos. It basically stabilizes everything, helping the training process run smoothly and, more importantly, much faster. It helps the model find the right answers without getting lost along the way, tackles a tricky problem we call internal covariate shift, and can even act as a little bonus to prevent the model from just memorizing the training data. It's an absolutely crucial piece of the puzzle. All right, here is the absolute key to how BatchNorm works. Let's say you've got this small batch of data about houses. BatchNorm thinks vertically, like it's looking down a column in a spreadsheet. So, to normalize the price for that first house, it doesn't just look at that one house, no. It looks at the prices of all 4 houses in the batch to calculate the average and standard deviation. This means the way one house gets normalized is directly tied to every other house in that group. So the process itself, it's beautifully simple. You grab a batch of data. For each feature, like price, you calculate the stats across that entire group. Then you normalize. It's elegant, it's powerful, but that core idea, that dependency on the entire batch, is both its greatest strength and, as we're about to find out, its fatal flaw. And now we get to the heart of the problem. Transformers, they deal with language. And language, well, it has a very specific problem that image models just don't really have to deal with. Think about it. Images are usually neat and tidy. They're all the same size, maybe 256 by 256 pixels, but language is messy. In the same batch, you could have a really long sentence right next to a super short one. Our computers, especially the GPUs that do all the heavy lifting, love working with perfectly uniform blocks of data. This is not uniform, and that's a big, big problem. So what's the workaround? Well, honestly, we kind of cheat. We take the shorter sentences and we just pad them out. We stuff them with these special, meaningless tokens. Think of them as just a bunch of zeros, until every single sentence is the exact same length as the longest one. Problem solved, right? Our data is now a nice, neat rectangle, and our GPUs are happy. But this simple little trick has a very nasty side effect. And this right here, this is where our whole mystery unravels. That seemingly innocent padding solution we just talked about, it absolutely breaks batch normalization. Let's see how. The source material gives us this perfect analogy that makes it all click instantly. Imagine you're a teacher and you want to calculate the average height of the students in your classroom. Simple enough. But for every student who's absent that day, you decide to just write down their height as 0. What do you think is going to happen to your average? Yeah, it's going to be completely wrecked. The true average height of your students might be something like 165 centimeters. But after you throw in a bunch of artificial zeros for the absent kids, your calculated average is going to plummet to something ridiculous, like 95 centimeters. That number is meaningless now. It's been poisoned by fake data you added just for convenience. And that is exactly what happens with BatchNorm. Remember, it's a vertical calculation? It looks down the column across all the sentences. It sees those padding zeros from the short sentences, and it doesn't know any better. It just includes them in the math. The average it calculates is now totally skewed, which poisons the statistics for the whole batch and makes the training go haywire. This whole problem is so significant that it actually has a technical name, Training Inference Discrepancy, or TID. It's basically the huge gap between the fake, corrupted stats the model sees during training and the clean, real stats it needs to work properly in the real world. The bigger that gap,
the worse the model performs. It's a disaster. So batch norm is officially broken by padding. The situation seems pretty bleak, but this is the part of the story where a new hero shows up, a different kind of technique designed to work in a completely different way. Enter layer normalization. Let's go back to our housing data for a second. Remember how batch norm looked down the columns vertically? Well, layer norm flips the whole script. It works horizontally. To normalize that first house, it only looks at the features of that one single house: its square feet, its number of bedrooms, and its price. The other houses in the batch, they're completely ignored for this specific calculation. And that right there is the entire game. Batch normalization creates this web of dependency. Every data point is normalized based on its neighbors. But layer normalization says, nope, every data point stands on its own. Each example is normalized completely independently. This tiny shift in direction, from vertical to horizontal, changes everything. And this is the elegant solution to our whole padding nightmare. Since layer norm works horizontally, it normalizes each sentence all by itself. Those artificial padding zeros in one sentence are never, ever looked at when calculating the stats for another sentence. Each sentence is its own little island. The poison from the padding is completely contained. It's just immune. And that is why it's perfect for transformers. So, case closed, right? Batch norm is for images, layer norm is for language. End of story. Well, in the world of AI, the story is pretty much never over. Just when you think everything is settled, a bunch of clever researchers start asking new questions.
And the new question on the block is this. If the real enemy here is that training inference discrepancy caused by padding, what if we could just fix that? What if we could make the original batch norm itself immune to the poison?
This line of thinking has led to some really cool new ideas, like something called regularized batch normalization, or RBN. It's basically a souped-up version of the original. It adds a clever bit of math, a penalty, during training that essentially discourages that big problematic gap from ever forming in the first place. It attacks the TID problem head-on.
And this leaves us with a really fascinating, open-ended question to think about. If these new techniques can actually fix batch norm's fatal flaw, could we see the old champion make a dramatic comeback in the world of transformers? The battle of normalization, it seems, is far from over. Thanks for joining me for this explainer.